Hello students, this video is about measurement uncertainty, which helps us answer the question, how well do we know our data and how well do we know our results? When we calculate with data, oftentimes we get these big long decimals, 0.157894736842105, and we often wonder, well, how many decimals should I include in a calculation? And when we're dealing with just made-up numbers, maybe that's a little bit arbitrary, and it doesn't really matter too much. But when we're dealing with real data that we have actually measured on a real thing, then it does matter, because there's only a certain amount of precision and accuracy that we can get in a measurement in real life. And if we were to show all of these decimal places as the result of a calculation involving that data, it's a little bit deceptive. It's implying that we have this huge degree of precision, that we know this value to this very, 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 very tiny level, when really we actually don't. So we need to come up with some rules on how to handle uncertainty in measurement. This is a spring scale, which we will be using a lot in physics. You can see on this spring scale that I start here at 0, and then here's 1 Newton, 2 Newton, 3 Newtons, 4 Newtons, and so on. The resolution on this scale is only about 0.2 newtons. So I have 0.2 newtons resolution on this scale. That is the smallest increment that I can measure on there. And if I get really tiny, and let's say I have a force measurement that's somewhere in between, I could sort of say, well, it's in between this line, and therefore it's going to be 0.7 newtons. So I can kind of get something in between there, but that's really all I've got. That's the best precision that I can, the best resolution that I can say I have with this scale is about 1/10 of a newton. That's my resolution. Anything smaller than 1/10 of a newton on this scale doesn't make any sense, because I can't actually tell you with any certainty that I have something smaller than that. So if I took this force value and then I did a calculation with it and ended up with this huge long decimal place, I cannot report that as a result because it's deceptive. I don't know the measurement to that level of precision. I really know it only to 1 decimal place. So let's get some rules for how this works. First of all, we have to think about 2 different kinds of errors. And these errors are going to result every time that we take a measurement or take data. And the first kind is called a systematic error. It's an error in the data that are due to incorrect instrument calibration, incomplete models, or some sort of bias in equipment or process. And let me go back to show you what I mean. Back on my spring scale over here, you'll see up here is this tab that I can pull up and down to slide the 0 marker up and down. And we do that so we can calibrate, well, what's going to be 0 force? What are we going to declare as 0 force? Let's say that I have nothing hanging on it, nothing at all. There's nothing pulling on this spring scale. I want it to read 0 newtons. That should be 0 newtons of force in most circumstances. But perhaps I didn't slide this correctly, and it's actually hanging out somewhere here around 0.4 newtons, the 0 line. So then every measurement that I make with this spring scale is always going to be 0.4 newtons off. There's a bias in the instrument. It's not calibrated properly. And we call that a systematic error. There could be some other errors that we've made in how we measure something. We're using an incorrect process. We're using a piece of equipment that doesn't actually measure what we think it measures. These could be systematic errors. And the problem with these is the advantage of these, at least, is that systematic errors are usually avoidable or correctable if you know that you made that error. An example would be, let's go back to my spring scale over here, and let's say I thought I was measuring force in newtons, but accidentally, being a human being, I made a mistake, and I was reading the grams side of the scale. And this is supposed to be for mass in Earth's gravitational field. So I thought I was measuring 3 newtons of force, but really I measured around 300 grams, and that's the value that I wrote down on my lab paper. I wrote down 300 newtons when really the scale was reading 300 grams, and I thought I was measuring over here in newtons. Well, that's easy to fix. If we realize that's the mistake that we made. After the fact, we could go back and divide all of our results by 9.81 to convert from mass to force, and we could get the real force value back out, even after the fact. So we could correct a systematic error if we realize that we made it. Random errors, on the other hand, are not correctable. And these are unpredictable errors because they're random. They're due to things like human error, incorrectly reading a scale, reflexes or judgment that don't let us measure something as accurately as we want it to. An example might be if I'm looking at this scale and the quote-unquote real force value is around 2, but I make a mistake when reading the scale and I actually write down 1.8 because that line is really close, or maybe I say 2.2 newtons. Either way, I could make some sort of human error that's unpredictable. It could go in either direction when I read the scale, and that's just a function of me making a judgment that's not quite correct. And if you think about reflexes and judgment, we think of things like timers, for example. When we try and time the start and stop of an event, we can't always hit the timer when we want to hit it, at the exact right moment when something drops or when something starts. So there's an error due to that reflex, that we have slow reflexes, nothing's perfect, nothing's instantaneous, and that's a random error. Random variations in testing conditions could be, let's say that I'm trying to measure the temperature of a beaker of water day after day after day. Well, that beaker of water is in my classroom, and every day is a different temperature outside. It could be 70 one day, and this is Boston, so it could be 40 degrees the next day. So, you know, there'd be this variation in the temperature of the water just because it's in an environment that's not consistent. And that would be another example of a random error. It's something we really can't control. We don't know which way it's going to go, and so on and so forth. So unfortunately, random errors are unavoidable, even if we know about them in most cases. Even if I know that I don't have instantaneous reflexes, that doesn't mean that I can time something accurately. There's always going to be some sort of random error every time I time something as a human being. So that's there. So even though we can't avoid them, we can reduce random error in the way that we set up our experiment. For example, in our class, in the Introductory Physics class before that you've probably taken, we've done a lot with timers where we know that timing something is inaccurate, so we take multiple measurements. We might actually use an average time of, let's say, 3 time measurements, and we take the average, and we hope that doing that smooths out the random error in any one particular measurement. So we take T1, T2, and T3. T3, there it is. And take the average, and hopefully the random errors in each of those measurements are sort of smoothed out by the fact that we're taking an average. We could also just get more precise instruments, but you know, on our budget that's not always possible. So we do what we can with what we have. So between experimental design and the equipment, we can hopefully reduce some of our random error. This brings us up to 2 different kinds of uncertainty and how we talk about the quality of our data. And we need to be careful when we talk about both of these terms, because the terms accuracy and precision we use in everyday language. Like, we use them casually, sort of to mean the same thing. Like, how accurate is your answer? How precise is your answer? But they actually have specific meanings in science, and we need to be sure that we're using those specific meanings, at least in our class. So accuracy is a measure of how small the systematic errors are, specifically the systematic errors. And another way of thinking about that would be how sure are we that we are centered on a true value? And I'm going to give you some examples down here in a moment to demonstrate the difference of this. So precision is how small the random errors are. So for each type of error, systematic and random, we have a measure of the quality of the data. Precise data is very consistent. It means we've reduced the amount of random variation in the data. They're very close to each other. And accuracy is about how well-centered they are, how they actually are they actually capturing the true value that we want them to capture. And the classic way of showing this graphically is through target practice. So I'm an archer. I love to shoot bows and arrows. I have a couple bows back in California, and so I've experienced all these sets. Unfortunately, more of this than I would like. But I mean, the ideal case is this down here in the bottom right, which is high accuracy and high precision. This cluster of hits, of shots, is accurate because they are centered around the true value, the target of what we want. And they're also very precise because they're clustered very close together. There's not a lot of variation in each particular shot. And so that makes them both accurate and precise. If we take a look up here in the top right, you see a set of shots that is very precise. I'm able to consistently hit in the same area over and over and over again. So you know my shot is pretty good. But there's something wrong either in the way that I'm sighting, something about my scope, maybe there's something wrong about the way I'm holding the bow, but there's a systematic error that even though I'm very precise, I'm not very accurate. All of these are clustered tightly together somewhere besides where we want them to be. They're not actually capturing what we want to capture. This case over here in the bottom left is high accuracy and low precision. It's accurate because it's centered around the right thing. We have the right idea here. We're just not precise. We're not able to hit that target consistently. So there's a lot of random error, a lot of random variation in the data that we have. And up here, of course, is the worst case. Low accuracy and low precision. These points are clustered around something maybe right around here, if I take a quick visual average. And so that's not the target. And they're also not very precise either. They're very spread apart, not very consistent, which means low precision. And this is going to lead to a lot of uncertainty in our measurement. If these are our data that we have taken about where is the center of the target, we really can't tell all that much from this data set, whereas we could tell a lot and be very confident about our results in this kind of a data set. Okay? Moving on. So we need to be able to quantify in some way how well do we know a particular number. When we show a number that is a measurement, when we show a number that is the result of a calculation, we have to have some way of saying, hey, folks who are reading this data, this is how confident we are. This is how significant we have for this number. Okay, so significant figures of a value is defined as the number of digits or decimal places we are sure that we know. These are the number of actual values that we're sure about. If we go back to what I showed you in the very first slide, all these digits, there's no way that we're sure about most of these digits. Most of these digits are not actually significant because they don't mean anything. It's just a result, a mathematical result of a computation. It's not something we actually know. So here are some rules on how to find the number of significant figures on a value. If these are confusing, don't worry about it. I'm going to show you some examples in just a moment. But our 4 rules are: 1, all non-zero numbers are significant. Okay, if the number is anything but a 0, it's significant. It's the zeros that kind of screw us up, and that can be very confusing. Zeros between non-zero numbers are significant. So, for example, if I have something like 1027, the 0 is actually significant because it's between 2 values that are significant, the 1 and the 2. Trailing zeros to the right of a decimal are significant. If I gave you something like this, all of these zeros right here, because they're right to the right of the decimal and they are trailing, they are behind the last numerical value, those are significant because they're telling me that I actually measured something to that level of precision. Trailing zeros to the left of the decimal are significant only if a decimal point is included. And I give you an example here. Let's say I have 700, but there's no decimal point included. I don't have actually that much precision in that measurement. I only have one significant figure. The only significant figure in this case is the 7. Because I haven't put a decimal, I don't know, did I measure something in a scale that's only in hundreds? And if I did, then I actually only know that it's 700-ish. Or did I actually measure something with a scale of 1, and it is exactly 700? And then I put a decimal after it, and then that's telling me as a scientist, okay, this person actually measured 700 exactly, and they have one all the way to the ones place of precision on that value. So if you include the decimal, these zeros become significant. If you don't include the decimal, they're not significant. Again, examples coming up. I'm going to come back to these in a moment. I think some examples would help right now. Here are some example values. And what I'd like you to do right now is pause this video and see if you can apply the rules we just went over to determine the number of significant figures in these values. Okay, did you figure them out? We'll find out. Let's take this first value, 48,923. These are all non-zero values. So if I look at rule number 1, I have several values that are, all these values are not zero, so they are all significant. There are 5 significant figures in this number. And if I wanted to write this in scientific notation, it would actually show me all those values. My decimal is here, 1, 2, 3, 4. I could write this as 4.8923 times 10 to the 1, 2, 3, 4 times 10 to the 4. I could write it like that, and then you can easily see in scientific notation that there are 5 significant figures because those are the only numbers that we have to show. That's the advantage of using scientific notation. Let's look at this next one. Again, only rule number 1 applies because all of these are not zeros. So 1, 2, 3, 4, there are 4 significant figures. Let's go to the third one. You can see here's 2 non-zero digits, so that's at least 2 significant figures. And I can use my rule number 2 to say that the rest of these are also significant because they are between 2 significant figures. They are between 2 non-zero digits. So these zeros are actually significant, and we have 5 significant figures. Now here's a tricky case. I know I have at least one because that's not a zero. The 4 is significant. Now these zeros right here, they're not trailing zeros, they're leading zeros. They're in front of the digit 4. And they actually don't give me any additional level of precision. Because if I were to write this as a number in scientific notation, 1, 2, 3, and 4, so I would be 4 times 10 to the 4th. You notice I only need one digit, the 4, to write that in scientific notation. So actually only one of those values is significant. Okay, those zeros are not significant right there. This isn't. I only have one significant figure of significance on that value. Now this one over here, I'm going to use my rules. There are 2 values that are not zero, so that's at least 2 significant figures. And then remember our rule that trailing zeros after the decimal are telling me something important. They're telling me that this is exactly 8.1000. I could measure out to this, and all those values were 0. I'm giving you an exact value. out to 4 decimal places. So this has 1, 2, 3, 4, 5 significant figures. And if I wanted to write this in scientific notation, I actually have to include all of those zeros. Of course, in scientific notation, this is just times 10 to the 0 because I didn't have to move the decimal place at all. So we usually don't write that because it's really redundant, and we just write the value as shown. 501.040, 501.040. I have 3 non-zero values. Those are automatically significant. I have 2 zeros that are between significant figures. That makes them significant, so that's 5. And this is a trailing 0 to the right of the decimal, which makes it significant as well. That's 6 significant figures. 3 million, unfortunately, I just have 1 significant figure here, just the 3, because I did not put a decimal at the end of this number, which tells the scientific reader that, hey, I don't actually know anything after the millions place in this number. Maybe I used a scale or some kind of units or some kind of instrument that only gives me millions, and I know nothing for any value smaller than that. So that's actually just 1 significant figure. And if you want to double check yourself, if you're not sure, again, write it in scientific notation. If we wanted to write this in scientific notation, I would have to move the place 6 times to get a million. So this number in scientific notation is just 3 times 10 to the 6. And you notice we only need the 1 value over here to present it in scientific notation. So it's just 1 significant figure. That's all we got. 10.0, another tricky one. Here's the 1 significant figure there, and it is just 1 because these zeros are not between any significant figures, and they're not holding any level of significance for us. It's just 1. And if you still don't believe me on that after checking our rules, once again, write this number in scientific notation. All you have to do is write 1 times 10 to the 1, and you can see that in order to express this value, we only needed 1 digit. We only needed 1 digit. So this is actually 1 significant figure. 340, same story as a million. I didn't put a decimal place at the end, so that 0 is not significant. I only have 2 non-zero values. So that's 2. And again, if you need to express it in scientific notation, we could do it like this. 3.4 times 10 to the 1st would be 340. Those are the same number, and we only required 2 digits to express the value. So it's 2 significant figures. 340 over here with the decimal place. There it is right there. So all of those digits are significant. We are telling the reader of our data that I actually measured to 340 exactly. So there are 3 significant figures on that value. Okay, so I'm going to pop back 1 slide real quick and cover these last things that I said I would come back to. The quick check is something I demonstrated. Write the number in scientific notation. Anything you have to keep, any digit you have to keep to accurately show that in scientific notation is significant. And that's a quick check. That's probably the easiest way to do it. And honestly, that's why we have scientific notation, is because it is very easy to see how many digits are significant, and we're not doing these kinds of rules trying to figure it out. So scientific notation is great. And calculations, this is kind of the last thing that I want to cover. The result of a calculation can only have as many significant figures as the term with the least number of significant figures. And the phrase that comes to mind when I do this is a weakest link. Right? You've heard the chain is only as good as the weakest link. Whatever is your least significant value in the whole calculation, that determines the number of significant figures in the answer. Let me give you an example. Let's take our top value here, 48,923, which has 5 significant figures. So 48,923, 5 significant figures. And I'm going to divide it by our value over here, 340, which is 2 significant figures. So if I divide this out, let me pull up a calculator real quick. So let's do this now. 48,923 divided by 340. Well, look, the calculator gives us all these decimal places. 143.891176.4 and on and on and on and on and on. So it gives us a lot of digits, but we don't actually know the number to that level of resolution. We just don't know it. So we cannot show all of those decimal places. Our least significant value is 340, and that only has 2 significant figures. So the best we can do is 2 significant figures. We only know this value to the first 2, 140. We actually only know this to 140. Okay, a more accurate way of doing that would be put our 2 significant figures here and then put it in scientific notation. The answer to this division problem is 1.4 times 10 to the first, or just 140. We don't know anything past that point. Okay, so answer with 2 significant figures, because the least significant value in the calculation was 340 with only 2 significant figures. So right now, do a quick check with yourself. You should be able to explain the difference between systematic error and random error and provide examples of each in the context of an experiment. So if I give you some sort of experiment, or you can even make up your own experiment of something you're trying to measure, can you tell me what might be a systematic error and what might be a random error? Explain the difference between accuracy and precision, and determine if a data set is accurate or precise. So if I give you a set of numbers and they're really close to each other, you might want to say those are precise. And if they're really far apart from each other, all over the place, maybe that's not so precise, for example. Now, determine the number of significant figures in a given value. Just go back to our rules. And report the result of a simple calculation using the correct number of significant figures. And what I mean by simple calculation is just like a basic addition, subtraction, multiplication, or division problem. Anything more complex than that we're going to be getting into later, but just focus on the simple calculation for now. And remember, folks, this is a video, so if you weren't sure about anything, go back, rewind, replay the parts of the video that you were unsure about, redo those examples, step through how I solve them out, and you can gain some more understanding that way.